Okay, so we've learned about vectors a little bit in the past. We've talked about how some quantities in physics can be described with vectors and some can be described as scalars. But we're going to learn a little bit more about how do we use vectors mathematically to solve problems that involve things like projectiles, because that's what our next unit is on. So before I get going, let's do a quick review here. So first of all, this is a vector, what I've got right here on the left. It looks just like an arrow, but it's got some qualities about it that make it special enough to call it a vector. So the first quality that it has is that it's got direction. The second quality it has is that it has magnitude. So if I were to take that vector and try to label where the direction is or where the magnitude is, the direction is this purple line, and it's really showing what direction the vector is pointed in. The magnitude is really about the length of the vector. So this is that quality we're very familiar with in regards to how much do you have. It's a number, it's a numerical value or a quantity. So magnitude is something that we're very, very familiar with. It's the direction piece that makes vectors a little bit different from what we've used in the past. So as long as we can remember that magnitude is really the length of the line, the length of the vector, and direction is indicated by the direction the arrow is pointing, that's really all the background we need on vectors. So moving forward, we're going to be adding and subtracting vectors. And in order to do that, we need some terminology. So wherever the vector starts, we call that the tail of the vector. Oops, I can spell starts. Wherever the vector starts, that's called the tail. And then wherever the vector ends is called the head of the vector. So you can remember it as the arrowhead is the head of the vector, and then the starting point is just the tail. So whenever we're adding or subtracting, we're always going to take our vectors and join them from tail to head. So let's say I was adding vector A and vector B, and I wanted to illustrate what that would look like on paper. I would have to take vector B and move it so that vector B's tail lines up with the head of vector A. So this works perfectly. So we can see that I'm going from tail to head, from tail to head. And if I had more vectors, I could continue to do that. But it's always a head attached to a tail, vice versa. Kind of like a human centipede type deal. Yeah, kind of gross, but it works. So my sum of these vectors, you might be wondering, okay, that doesn't look like a normal vector anymore. The sum of these vectors would be the connection from the very, very beginning to the very, very end. So this would be the sum from the very first tail to the very last head. So that's what adding and subtracting vectors looks like, is we're literally taking them and joining them together in a very specific order, tail to head. Now when we're adding, it doesn't really matter what order we add in. So let's say we had a vector A, I'm going to add on here, we had vector A and vector B, and they were getting added together. We could add vector A first and vector B second, and we get this nice orange sum. Or over here on the right, we could add vector B first and then vector A, and we're still going to get the same orange sum. I can see that this orange vector is the same length as this orange vector, and their directions are exactly the same. They're parallel. They're pointing in the same direction. So these two orange vectors are in fact the same, which means whether I add vector B and vector A together in this order, or I add them together in this order, it doesn't really matter because I'm still going to get the same sum. Now when we're subtracting, we have to do something a little bit wonky. We have to reverse the direction. I'm going to highlight that because it's very important. We have to reverse the direction of the vector that's being subtracted. So after we reverse the direction, we just still add tail to head. It's the same process. It's really just the reversing the direction that's a little bit different. So let's say we were trying to do vector A minus vector B. Since vector B is the one that's being subtracted, we would have to reverse the direction of vector B. Here's what that looks like. That literally means we're taking vector B and inverting it 180 degrees. Its magnitude is still saying the same, but by inverting it 180 degrees, it is now pointing in the exact opposite direction that it was before. So we call this vector negative B. And negative B is what's here in my problem. So now instead of thinking of this like subtraction, I can think of this like addition. I'm taking vector A and I am adding it to negative vector b. And adding is very simple, just drawing them tail to head, tail to head, tail to head. And when I do that, I end up getting the sum here from my first tail to the last head. And that sum is really the difference between A and B. So subtraction is really just addition, but before you can add, you have to figure out what this negative vector is by reversing the direction. Now, let's say we were actually putting numbers to it, because this has just all been qualitative, just drawing sums and differences. But let's say we wanted to actually calculate the sum or the difference between vectors. When we're drawing a vector, we've talked about this before. You have an x component and you have a y component. Now we've just always labeled them x and y, but if we were being specific and this was vector A, we could say that this is ax and ay, just to say that, you know, it's the x component and the y component. I hate drawing my a's that way, so I'm going to erase it, but you get the point. A vector can be broken up into two components, an x component and a y component, and you can treat the x component like a tinier vector, just in the horizontal direction, and you can treat the y component like a tinier vector, just in the y direction. Now, when we're adding vectors together, we're taking our x components and adding them up, and we're taking our y components and adding those together. But we're not taking x's and adding them to y's. We're just taking x's and adding them to x's and y's and adding them to y's. So let me show you a picture. Oops, didn't mean to move them. Let's say we were trying to add two vectors, vector A and vector B. We would draw them tip to tail. And if we wanted to draw the sum, we could draw the sum by connecting the very, oh, did I say tip to tail? I'm sorry, I meant tail to head. We could draw them tail to head and then connect the very tail to the very last head like this. But that won't really give us numerical values. So instead, what I'm going to do is I'm going to break up my vectors into x components and y components. And when I do draw my sum, my resultant vector is what we could call this orange vector, but I'm going to call it my sum. When I draw my sum, I can add up both of the x's and add up both of the y's, and that'll get me my total x component for this sum and my total y component for this sum. So let me show you again. I'm taking my two y's and adding them together literally through drawing and literally numerically. 13 plus 7 gets me 20. And then I'm taking my x components and adding them up literally by drawing them tip to tail or tail to head, and then adding them numerically. 8 plus 26 gets me 34. So once I have these components, now I know everything I need to know about my sum. It's not just a picture that I have. I know the x coordinate and the y coordinate for this sum vector. Now let's say that we were multiplying a vector by a scalar. Remember, a scalar is just a number. It's only got magnitude. It has no direction associated with it. So let's say that we were multiplying vector m by the scalar 3. So vector m, we've got drawn here in black. If I were to multiply this vector by 3, what I'm effectively doing is I'm taking my x component and multiplying it by 3, and I'm taking my y component and multiplying it by 3. And we've got the work shown right here. So if my m vector was 7, 3, what that means is that the m vector used to be 7 across and 3 up. If I'm taking these two components and I'm tripling them, multiplying them by 3, now I'm going to have a new x component. And I don't even have room to really draw it to scale on here, but they've drawn it to scale over here. But what I'm going to end up having is I'm going to end up having a new x coordinate that's 21 and a new y coordinate that's 9. but my vector's direction is still going to be the exact same. All that's really happened is it's gotten longer. And in fact, it's gotten longer by a factor of 3. What I'm doing is I'm effectively tripling the size of this vector. So when you take a vector and you multiply it by a scalar, what you're doing is you're just taking the magnitude of that vector and multiplying it by a scalar, which is what we've got drawn right here on the left. Now let's say that we wanted to find the magnitude or find the components of a vector and it was unknown to us. We were just given limited information, but we wanted to calculate it. So the magnitude of a vector is the length of the vector. Now the notation that we use for magnitude is a little weird. So let's look at this picture here. We've got vector A right here. If I wanted to find the magnitude, I know that magnitude is referring to the length of this line right here. I can write this with some bars. What I'm saying when I write vector A in 2 bars is I'm finding the magnitude of vector A. So this is referring literally to magnitude. It's a length. Or I could write vector A between double bars, and that's saying the same thing. So if someone were to come across either of these notations, they'd have to know that these are both referring to the magnitude of vector A. Now, the reason I have this vector drawn on this graph right here, what I'm hoping you're seeing, is that it looks an awful lot like a triangle. If I were to take my x components and my y component and connect it to vector A, you'd see that this is a 90-degree angle. This is a right triangle. Now, we can do a lot of useful math with right triangles. In fact, Pythagorean theorem is one of them. So you may remember in geometry learning about a squared plus b squared equals c squared. What that means is your side lengths squared added together equal your hypotenuse squared. Well, my hypotenuse in this case is the magnitude of my vector. So the magnitude of my vector squared is going to equal my side lengths, x squared plus y squared. Now, if I wanted to find just the magnitude, not the magnitude squared, I could take the square root of both sides of this equation. And that would get me just the magnitude of A isolated. And this would be equivalent to the square root of x squared plus y squared. So this formula is a formula I'm going to use pretty frequently when I'm trying to find the length of a vector. Now let's say I didn't know what x or y was. They were unknown to me. But let's say I knew what my theta was and I knew what my magnitude was. I can use trig functions to find my side lengths, just like I can use trig functions to find the side lengths of a right triangle in geometry. It's the same thing because vectors are very, very similar to right triangles because they kind of are right triangles. So I've got my sine function, which is equal to my opposite side over my hypotenuse. And if I were to look at this triangle, my opposite side is my y component. So sine is really equal to y over my hypotenuse, which I know now to be the magnitude of vector A. So if I wanted to find y, I could take both sides and multiply them by the magnitude of vector A. This would isolate y and get it all by itself. So your y component is really the same thing as the magnitude of A times the sine of theta. So if you know your magnitude and you know the angle of your vector, you can find the y component. Now this also applies for our x component. So cosine is equal to my adjacent side over my hypotenuse. My adjacent side in this case is my x component. And my hypotenuse I know now to be the magnitude of my vector. So if I were to isolate x, I'd have to multiply both sides by the magnitude of A. So I'm going to have the magnitude of vector A times the cosine of theta equals my x component. So if I know magnitude and I know theta, I can find my x component. Now let's say I didn't know my theta. Let's say I knew all of my side lengths, I knew x, y, and I knew my magnitude, but I didn't know theta. Our tangent function is actually very useful in finding theta. Let me show you how. I know that tangent of theta equals opposite over adjacent. And we just talked about how the opposite side length is y and the adjacent side length is x in this particular picture. If I wanted to solve for theta, I could use what's called an inverse function. In this case, inverse tangent. And what the inverse function does is it literally inverts your inputs and your outputs. So it switches this y over x with theta, and it switches theta with y over x. So in your calculator, you could plug in the inverse tangent of y over x, and you would solve for theta. And this would be an effective way of finding your angle for your vector. So I didn't do any examples in these notes. I just went through a lot of the procedures and the notations. I would recommend going through some of the example videos before moving on to the homework, just to make sure you've really got it.